Welcome to Heat and Thermodynamics. I want to have a look at calculations involving the areas of heat in thermodynamics, and this is part 1 of these calculations. Our interest here is to have simplified lectures on these examples that will enable you to understand better the concept of heat in thermodynamics. Let's move to Question 1. Now, this question is focusing on determination of entropy by a statistical mechanics approach, where we shall be focusing on aspects of microstates, and then we solve this question. So this is an example generally used to help you understand the most basic approach of this microstate use in calculating entropy of systems. 3 particles are in a system illustrated below. This is the diagram. You can see the energy levels. So we are talking about the total energy contained within the system is 5e. So if you have a number of particles in here in this system, the sum of their energies should total to 5e. Determine the entropy of the system given the Boltzmann constant as 1.38 times 10 power minus 23 joules per Kelvin. Now this will take us to thinking of the microstates, the number of microstates that these particles are likely to settle in when you think of this system and the energy limits. So first we have been told about 3 particles. So think of it, 3 particles which are distinguishable. So we have a possibility of the particles getting arranged in this system in such that we have particle A at level E, particle B at level E, and then we have particle C at level 3E, totaling to 5E. That is 3E plus 1 plus 1, that is 5. There's a possibility of having B at 3E and C back to E. That is a case, that's a state which is possible in this system. The third state which is also possible in this system is when now the particle A in the system is at 3E, the rest settles at E. And then you think of another situation where we have the particles settling at, with having A at E, but then the rest at 2E. So that will be 2 plus 2, that's 4, plus the 1 at E, that's 5. Remember, the total is supposed to be 5E as our total energy of the particles in the system. Then this also, we can alternate in the positions so that we have A at 2E, C at 2E, but B at the E level. Then finally we have A and B at 2E, then C at E. There is no any other extra possible state that this system can occupy to have a total energy of 5E. So this simply means that we have 1, 2, 3, 4, 5, 6 microstates. So the number of microstates here is actually 6. We normally represent this by omega. So entropy in this approach can be calculated by Boltzmann constant natural log of number of microstates. So we have 1.38 times 10 to the power minus 23 times natural log of 6. And this will give us this by just basic calculations or use of a calculator. Question 2. The question 2 says, glucose, which is comprising of carbon, hydrogen, and oxygen, in this number of atoms indicated, is the main fuel metabolized in animal cells. That's true. How much energy is given off when 100 grams of glucose react in the following equations? You can see the equation where you have oxygen added to this, then you end up with carbon dioxide and water. And enthalpy change as minus 2,799 kilojoules. So the question here is, if you look at this equation, you can tell the ratios of reaction, and that can help us know the moles, and from there we can use the molar mass and grams to know what amount of energy can be given out, or given off when you have a specific number of moles of glucose in the reaction. So in this case, we are being told if we talk about 100 grams of glucose reacting, how much of this energy will be given off based on this equation. So let's look at the answer. So we have to think of the molar mass of glucose first, taking carbon to be 12 times 6, because we have 6 of them in this formula, plus that of hydrogen, which is 1. These are atomic mass units, but we can do our estimation in terms of what we have. Then we have 12 times 1, and then 6 by 16, which is basically oxygen contribution. We are leading to 180 grams per mole. Now, moles of glucose that reacted is supposed to be now the mass in question over the molar mass, because we're talking about the molar mass giving us grams per mole. So how many moles will we get from this? So we divide the 100 by 180 to get 0.556 moles. Now from the equation above, this equation here, you can see in terms of if this equation is fully balanced, you realize that 1 mole of glucose actually led to the production or giving off of minus 2799 kilojoules. So if this is the case, then we can talk about equivalence. So 1 mole is equivalent to that. Then what about 0.556 moles from our calculation? This results into 0.556 times minus 2799 over 1 to give us minus 1555 kilojoules. You can know why we talk about minus here. If you go back to classification of entropies and heat enthalpy changes, at what point do we have positive and at what point do we have negative, and what that means, because we have exothermic and endothermic reactions, and that is basically where we get the meaning to the minus. Question 3 talks about a Carnot engine, and we are told that 63.9% efficient Carnot engine performs 1.05 kilojoules work while operating within 2 heat reservoirs. Calculate the quantity of heat supplied by the hot reservoir. Remember, the hot reservoir has to cause some work done, and the cold is actually supposed to take away the heat that was responsible for the work that was done. We call positive work and negative work. So basically, if you understand the Carnot cycle, efficiency is one of the most important aspects when you talk about these engines that works with the principles of Carnot cycle, doing work by supplying heat. So here we want to use a simple equation where we simply say that efficiency, thermal efficiency, that's why we write this, TH, equals to work output over the heat input. There are other formulas to this, but this is actually what is more relevant to us. And remember, we have efficiency as 63.9 over 100, that is percent, equals to the work output. Already you can see the work performed is 1.05 kilojoules, that is 10 to the power 3 of joules, over Q, which is the heat supplied. So making Q the subject of the formula, you'll end up with Q equals to 1.05 times 10 to the power 3 times 100 divided by 63.9. This by a calculator you get 1643.19 joules. Very simple way of looking at this question. Question 4. It's taking us to work done in a thermodynamic system. And when we are dealing with gases, especially ideal gas, the gas equation is going to be very key here. And there's some aspect of borrowing from the first law of thermodynamics, where internal energy is one of the variables or parameters to be considered. The heat capacity at constant volume of iodine gas is 87.3 joules per Kelvin. Given that for a system of iodine gas, the internal energy is expressed as this, that is U equals to 3 is a constant, N number of moles for that gas, R is universal gas constant, which is 8.314 joules per mole per Kelvin, or we have other expressions depending on which unit you choose. And then T is now the temperature. That is, depending on which thermodynamic system you want to refer to, this may be a constant or not. Calculate the internal energy if the temperature of the system is set at 27 degrees Celsius. Take the R value to be 8.314. Now the key equation here is the expression for U. If you look at the solution to this, U is 3 nRT, and you know that heat capacity at constant volume is expressed as differential of U by dt, which if you apply that on 3 nRT, then you can only see when you differentiate U with respect to T, you will get 3 nR because T is the variable. And if you do that, you get 1 differentiating with respect to T. So 1 times this constant leads to this. And if we are already given that the heat capacity at constant volume, CV, which is found by this differential, is actually 87.3. So means 3 nR is equal to 87.3 joules per Kelvin. So we can find N, because 3 is a constant, R is a constant, we know all this. So N, which is the number of moles, is 87.3, which we have, over, divide both sides or throughout by 3R. So 3 times R, which is 8.314, giving you 3.5 moles. Now, having found N, we are only remaining with T as the unknown in this equation. So at T, 27 degrees Celsius, then we can find U for that system. So T, 27 degrees Celsius, we need to convert this into Kelvin by adding 273.15. And if that addition is done, then you end up with U equals to 3 times 3.5 times 8.314 times 300.15, which is the Kelvin version of 27 degrees Celsius. And all this will give us joules. And if you do key in this into a calculator, you quickly get 26,202.19 joules as the answer to this question. As you can see, they are actually very simple questions and you can easily address them. Question 5. Suppose 5.0 moles of an ideal monoatomic gas expand at a constant temperature of 22 degrees Celsius from an initial volume 2.0 cubic meters to 8.0 cubic meters. How much work is done by this gas? Okay, so work done, which is also another factor, another parameter to consider in first law of thermodynamics, tells us that, how do you calculate work done for a system of gas or a gas system? We find this equation, which is common, that we know we find to find the integral and the minus integral from initial volume to the final volume of PdV. Now this PdV is actually the expression for work done when you're talking about an ideal gas or a gas in a thermodynamic system. So we talk about this as minus nRT ln Vf over Vi. This natural law comes from the fact that, V is the only variable here. Pressure, remember this, we can associate it with the expression for ideal gas, which is PV equals to nRT. Okay? And P is what is given here. So making P the subject, we will have the expression as P equals to nRT over V. Now, if you substitute the place for P with nRT over V, you'll end up with 1 over V as a variable to subject this integral. And when you subject an integral to a reciprocal, that translates into a natural log of that variable. So you end up with ln of V minus, if you have now V final, that means ln of V final minus ln of V initial. And when you deal with natural logs when subtracted, that is where this division is coming in. So if you have minus nRT ln, or natural log of Vf over Vi, basically what is going to happen here next is just keying in the values. So N is number of moles, we had 5, this is it. and R is a constant we already talked about earlier, that is 8.314 times the temperature here must be converted into Kelvin. We are talking about 22, so 22 plus 273.15, you get your Kelvin, in your temperature in Kelvin. Then we have ln of V final is 8, V initial is 2, then you end up with this value as the work done by this gas. Question 6. Heat transfer per unit area between two large parallel plates. This is actually thermal conductivity. So we are talking about heat transferred between two large parallel plates is 138.53 watts per square meter. The plates are 2 centimeters apart. That's a separating distance between the plates. So if plate 1 is at temperature 290 Kelvin and plate 2 at temperature 150 Kelvin, determine the coefficient of thermal conductivity of the material between the two plates. So we are talking about rate of heat transfer given by the formula Q is equal to K A delta T over L. This is actually the separation between the plates, and this is the change in temperature. And heat transfer can only be possible if there's a temperature gradient. So there's a hot point and a cold point that there will be transfer of heat from the hot region to a cold region. So that rate of transfer is actually given by this expression. Once you get this expression, in our calculation, we have been given the heat transfer per unit area. That means the expression of Q over A, which you have down here. The expression for Q over A is actually K delta T over L. And this is already given as a value 138.53. So what do? Our interest here is to calculate K, which is the coefficient of thermal conductivity. So our interest here is to make K the subject of the formula by first getting this expression. So you say K delta T over L equals to 138.58 watts per square meters. So K itself will be L times this value over delta T. And L we know was 2 centimeters apart. You convert that into meters, you'll end up with 0.02 meters times 138.53 watts per meter square, all over the difference in temperature. The temperature at hot point is 290 Kelvin. The temperature at cold section is 150 Kelvin. That difference will give you about 140. Divide the value you have up here by the 140. You'll end up with 0.01979 joules per second per meter per Kelvin as the coefficient of thermal conductivity. Remember, it's normally referred to as a rate. That's why you see this aspect of time in your calculation or in your result as your units. Question 7. 0.2 kg sample of a metal is heated to 600 degrees Celsius. Maybe it is put in some oven. It is then placed into a 0.5 kg water in a calorimeter at 15 degrees Celsius. The water is contained in a 0.15 kg calorimeter cup made of aluminium. The final temperature attained is 35 degrees Celsius. Calculate the specific heat capacity of the metal, given the specific heat capacity of water as 4182 and that for aluminium as 900. Now this is a quantity of heat problem, and when you're dealing with this and it's under calorimetry, there are so many assumptions made as far as matters heat transfer and heat losses are concerned. So we first want to assume that all the assumptions are kept, and therefore whatever heat is lost in the system must be gained by some components of the same system. And the overriding equation that we are going to use is Q for quantity of heat equals to mc delta theta, where m is actually the mass of any of those members of the system, c is the specific heat capacities, and delta theta is changing temperatures. Now we are asked to calculate the specific heat capacity of the metal. So let's call it Cm. And for this formula, this metal is what is losing heat. Remember, it was heated at 600 degrees Celsius. So it has to lose some heat to the water in the calorimeter. And that is actually because the water is contained in the calorimeter, the heat change is also affecting the material, the aluminum material of the calorimeter, the cup. So we say the heat loss actually is calculated by specific heat capacity of the metal times 0.2, which is its mass, times the temperature change here. Remember, we have been told that final temperature, or what we can call equilibrium temperature of 35 degrees Celsius, was attained by this. So we have a changing temperature from 600 to 35. We expect a negative here, but we want to keep things positive, and this can still lead us to a positive answer when you're talking about the Cm. So we'll have Cm times 0.2 times 600 minus 35. And this will be equivalent to whatever is gaining heat here is, we have water gaining heat, and we also have the cup gaining heat. So the mass of water was given to be 0.5, right? So that is 0.5 times the specific heat capacity of water is given here as 4182. And then times, what is the temperature change for water? Initially, the water was at 15 degrees Celsius, and we are getting an equilibrium temperature at 35. So the difference here will be 35 minus 15, that's change in temperature. That's for water. Then remember, whatever is gained by water, there will be some gain that is experienced by the aluminum cup. So we want to get to the mass of the cup, which is 0.15 times 900, which is the specific heat capacity of aluminum, the material for the cup. And the temperature change for the cup is the same as the temperature change for the water. That's why we have 35 and we have 15. So we have this difference multiplied by this and this. All this you add to whatever you shall calculate from this other end. That leads us to a value of 41,820 for the water and 2,700 for the cup. And you add all this, gives you the total heat that is supposed to be gained, and this is equivalent to what was lost. So if you do these calculations, you'll end up with 113 cm equals to 44520. So divide throughout by 113, it will give you the value for cm, which is 393.98 joules per kg per Kelvin. That basically is the way to approach questions of that nature. There's some examples which talk about electrical heating and stuff, and that will demand for another approach for the rates for energies in terms of electrical supplies. For this case, we're just talking about general heating, where that leads to temperature changes. That was the section for part 1, and we have other parts. We wish that you do subscribe and like, so that we can have this message shared with many, and you as well. When we get to upload another part of these calculations, you will be able to also be notified and get to learn and understand these concepts of physics. Thank you very much. Thank you for your support.